Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be looking at Chapter 8 of the lecture notes, Polynomial Regression. Now, polynomial regression is a way to use curves, fairly simple curves, polynomials, in the fitting of regression lines to data. So let's take a look at what a polynomial model looks like when we have only one predictor. So recall that a polynomial is an expression where we are relating a response variable y to a variable x, but we have powers of x. So think of x by itself as x to the first power, and we're going to add to that a term of x squared all the way up to xp, where p is the degree of the polynomial. And so if p, the largest power, equals 1, then you're left with only with the simple linear regression that we are accustomed to. But if p is larger, say 2 or 3 or higher, then we have a polynomial that has all those curves in it. So let's look at an example of a second and a third order polynomial that would be a quadratic and a cubic equation. We'll come back to the code in a moment, but here's a couple examples of a quadratic equation. It's a parabola. It's a sort of a U shape, and the U can be facing up, sort of convex, or concave. A cubic. Here's two examples of cubics. It's sort of like a little bit of a lazy S, though it doesn't have to be very lazy at all. But it has two inflection points, right? It starts sort of concave down, and then it switches. It has an inflection point right here where it goes from concave down to concave up. And similarly, this dashed line starts off concave up, and then has an inflection point around here, and then it becomes concave down. And the variety of shapes that these can take is quite remarkable, though the main feature is about whether the concavity changes or not. So quadratic either is strictly concave up or concave down, whereas a cubic changes in the middle there. And these equations, just to take a quick look at the code for this, to be honest, this does not look very necessarily very helpful. But here is the first curve, the first quadratic curve. It's x squared minus x5. So if I page down for a moment, okay, oh boy. So minus 5 is the intercept for this, and x squared, we have this quadratic term. The second equation, this dashed line, which is concave down, notice it's offset left and right. Its maximum is around x equals minus 1, and where the y value equals positive 3 right there. And so here we have an offset of 1, and a minus 3 positive 3 was the value of y there, and the minus sign in front of the x squared term gives us the concave down. All right, so this is all sort of review, I hope, in terms of writing polynomial equations. So it's important to recognize that not all, or even none, of the turning points of a polynomial may actually be observed in the range of x. In fact, if your data, you could have data over here to the right which has this sort of positive curvature, okay, sort of concave up, and your data could be over here, and a polynomial could show you that. It could, but you'd fit the whole polynomial to the data, but the data maybe only exist in one sort of tail of that curve. All right, so the basic idea here, and we're always using this in statistics is Taylor's theorem. Taylor's theorem basically says that when you look up close at a surface, regardless of how wiggly that surface is, if you look up close enough, it's going to look pretty flat. And so that's why we start off by fitting straight lines to data, because it's a very simple expression of data, of the mean of the data, and up close enough, sort of if you zoom in enough, it's going to be flat, at least in a bounded region. Now, as you zoom out, you see more of the wiggles. Those wiggles can be described by a polynomial, and even the most complicated sort of continuous, at least differentiable curves can be described by polynomials, or at least be approximated in that way. And you can show mathematically that if you had n observations, that if you had an n minus 1 degree polynomial, that you would fit the data exactly. In fact, let me scroll up for a moment. Okay, so say you had n observations, and you had an n minus 1 degree polynomial. So that means this p would be n minus 1. So just for the sake of it, let's say we've got 10, actually let me see what example I used below. I think I've got 11 points. So if n equaled 11, then p would equal 10. Well, if p equals 10, how many coefficients do I have? So we have 1 up to 10 plus beta naught. So we have 11 parameters, and we have 11 points. So we have all the flexibility we need to actually fit the data exactly. So if I scroll back down to that point, we can show mathematically that an n minus 1 degree polynomial will fit the observed data exactly, because we have as many degrees of freedom, as many betas as we do observations. And because we fit the data exactly, we'll have an r squared value equal to 1. So all this code here is just creating sort of a random scatter plot of x and y points, and then I'm constructing all the x1 up to x10 polynomial terms, and then I'm fitting a linear model with x squared, x cubed, all the way up to x to the 10th power. Okay. And then what are the coefficients of this model? Here's the beta naught, beta 1, beta 2, and you can see, oh my gosh, like for a set of random numbers which are drawn from a normal distribution with mean 0 and standard deviation 1. Okay, so basically these points are fitting in a little square from -2 to +2 in both the x and the y directions. But look at some of these coefficients in the 10,000 range, like almost 100,000, -100. Crazy, absolute crazy. Let's plot this data. That's what all this stuff is doing. And on the right hand side, here's a plot of the data. In fact, it's, I didn't even make my axes tall enough, but notice these 11 points, they fit in a little square. In fact, on the left hand side we've got a square that basically goes from -1.5 to +1.5 in both directions, and that's our scattered plot of points. Okay, if you were to fit this with a straight line, and in this case, even though both x and y values were random, it looks like there's a slight negative relationship here, no big deal. But fitting this with a high order polynomial, you get the curves that just sort of spike up and down, but the curve goes through all the data points. And on the right hand side we sort of see that a little more clearly, but look at the range. We go up to 10,000 on the y-axis just to sort of accommodate most of the curve, not even all of it. So, and when you zoom in, yeah. So imagine if you're trying to make a prediction. If you want to predict a value at x equals +1/2, what's the best prediction there? Well, based on this model, it would be right about there, and depending on how steady my hand is, that would be about 2,000 on the y-axis. So fitting a very high order polynomial gives you basically nonsensical predictions between your terms. So Those are things to watch out for. You can predict your observations perfectly, but who cares about that? We really want to understand the relationships between variables, allowing for some variability. All right, so let's look at an example. Oh, you know what? I'm going to say one more thing here. Another concern is the importance of the lower order terms. That is, we've got all the way up to xp, but to support xp, we have x to the p minus 1 and down to x squared and down to x. And the scale of x will actually determine the importance, that is the significance of the lower order terms. So whether beta 1 is important for the slope and beta 2 for the quadratic and so on, whether those terms are significant in the model depends on whether you measure something in meters versus feet or pounds versus kilograms or things like that. And so one strategy for, so here I've got an example having time of a reaction. For a chemical reaction, we have temperature. So we could measure this in Celsius or Fahrenheit, and the significance of beta 1 will could be different depending on which scale you use, or Kelvin even. And so one strategy when you are modeling something with a polynomial is to center the data. And saying center, the default for this is you would subtract the mean off of all the values of x. So if the average temperature in Fahrenheit was 70 degrees, roughly comfortable, springtime room temperature, then if you had an observation at 50 degrees, it would be 50 minus 70, or negative 20. And if another observation was 80 degrees, you'd have 80 minus 70, which was positive 10 degrees, and so on. So you'd subtract that from all your observations. In R, what this would look like is a new column. So you'd have all your temperatures x, and then you'd create x dot center or something like that, a new column, and you'd set that as x minus 70 degrees, for example. Or you could do actually explicitly x minus the mean of x. Okay. I recommend restricting your attention when you do polynomials to fairly low order models. Typically if you've got a little bit of a curvature, you can do a quadratic model. Just include an x squared in there, and that is enough. A cubic model, and certainly a quartic model, that's sort of getting a little bit crazy, in my opinion. And man, if you're not fitting the data with a fourth order model, if you've got wiggles, too many wiggles, then I would consider a transformation, or think more carefully about what's actually describing the pattern in the data. Pay really close attention to diagnostics in these high order models, because a single observation can determine whether you need a quadratic model versus a linear model. Single observations. So things are really become pretty sensitive with polynomial models. And when you are doing model selection, there's a hierarchy of the powers of x, right? So if you're going to include the x to the p term, you want to include all the lower order terms as well, regardless of whether they're significant or not, because that entire polynomial depends on those lower order terms. And then, of course, when you start removing terms, you have to start with the highest term first. So start by removing x to the p, and then x to the p minus 1, and you stop when that highest order term is still significant. Okay. In SAS, we're using R, we're not using SAS, but there's, this is a problem when you do backward selection, that the model selection procedures themselves typically do not retain the natural hierarchy, but will simply drop terms, the least significant term first, and it could be that the highest order term is not the least significant. So you may have to, in these cases, perform model selection manually. So you fit the model, then you actually manually type in what the next model is and fit that one, and so on. All right, so let's turn our attention to an example. And it's an example that, to be honest, I've never spent the time to actually understand. That's it's a crazy thing to admit. But this is a chemistry example. So we've got something called cloud point versus the percentage of I8. Okay, so the cloud point of a liquid is a measure of the degree of crystallization in a stock or some material, and it's measured by the refractive index. So if your liquid is starting to crystallize, then when you send light into it, it will refract in a certain way, and that is a measure of that cloud point. It's been suggested that the percent of I8, which is a something I could make up, but maybe you'll look it up, in the base stock is an excellent predictor of that cloud point. Okay, so this stock that you're making this liquid from includes some component called I8, and it's a percentage of that that we are caring about in terms of predicting this cloud point. And so, for example, if we were looking at a quadratic model, we could do the cloud point as a function of I8, and we have a linear term and we have a quadratic term for I8. So we've got some data, and if I bring the data up, fairly simple data set. We've got I8, so going from 0% up to 10%, and we have the cloud points, roughly ranging from 20 to 30. And if we plot the data, we see we've got some replication in terms of the I8 values, because we've got 2 points in some of these. Here we've got 3 points on this one, and we see a bit of a curve here. So there's some options here. We could transform either the x or the y variable, maybe by taking the square root of the I8 variable, or maybe the log of I8, things like that. But the purpose, of course, of this chapter is to look at polynomials. So if you were to trace a line with your pencil about following the sort of the center of these points, looks like there's maybe a little bit of an up curve on this last point, but it is, of course, just one observation at the extreme value of I8. But you do see this sort of curve, this downward curve through most of the base of these points. You'd have to think about what model fits this. Maybe not a straight line, maybe something with a downward curve, but then we also have this last point which suggests a bit of an up curve. So it could be either a quadratic, that is a polynomial to the second power, or a cubic, a polynomial to the third power, which would allow this curve up at the last, for this last observation. One thing that I did here, you can see, as you noticed on the horizontal axis, if it's not hidden behind this garbage, is that I've centered the data at 0. So I've done that thing where I've taken I8 and I've subtracted the mean. And I've actually done this destructively. I've actually overwritten the original variable I8 rather than creating a new variable. So we've got our centered I8 variables as the predictor. All right, so let's just fit a simple linear regression fairly naively and take a look at the residuals. Now there's several things going on here. The first thing we notice is that relative to the predicted values, we see this curvature. Similarly, relative to I8, we see curvature. And so once we see curvature here, that we're not capturing the mean of the data, we don't really care about influential observations or normality or any of that. We haven't even captured the mean of the data. Stop. Fix whether you capture the mean before you think about influential observations. This influential observation number 1, okay, which is this point down here, is not really interesting because, yeah, we're not capturing the mean. So why focus your attention on one observation? So let's start with the most complicated model that the data suggest, as I page up back to this plot. Right? If we see sort of a downward curvature for most of the points and then this upward curvature for the last one, that would indicate something like a cubic model. If I page way up, okay, sort of like this solid line here, but with less extreme curves. Sort of curved down and then curved up. Page way back down. All right. So there is a function in R called capital I, which is used to create an interpreted object and treat it as is. And this is sort of a shorthand way of using a single variable and creating new variables in a model. So we've got I8, we've got I8 squared and I8 cubed, and those will be individual terms in the model. This allows us to include these higher order terms without creating new columns in the data set. All right, so we'll assign that to I3, meaning 3 is the third power. So that's our indication of what degree polynomial I've got. So if we look at this equation, or rather the summary table, here's the intercept. Right, this is the predicted value of the cloud point when I8 equaled 0. Then we've got the linear term, the quadratic term, and the cubic term. And the only hypothesis test here that's very interesting is this highest order term, which turns out in this case to be significant. So so far, it looks like a cubic model is pretty good. By the way, look at this multiple r squared. This is what you get when you study chemistry and physics. You get these very high degree of relationships. All right, let's take a look at our residual plots and see what we think about our model. The residuals versus fitted values look pretty good, and versus the cloud point or the I8 values. Looks like we have potentially one influential observation, number 1. Number 18 is a bit influential, but mostly because it has high leverage. 14 is equally influential, and those two are the points that have the most leverage. Normality looks pretty good, and in this case we don't really know the order of the data actually collected in the experiment, so I'm not sure that there's much interest in this plot. So one comment here, I think I made it above here. The output below shows that the cubic term improves the fit of the quadratic. Furthermore, no individual point is poorly fitted by the model, though case 1 has the largest residual. And let's go back to that data briefly and see which. So the first observation is at 0 with 22.1. Can that be true? This seems to be the most influential observation. Okay, it seems like that could be a bit of an outlier. Okay, if I page back down, that's this point here. Okay, that seems reasonable to me. So the first and the last observations have the lowest and highest values of I8. Okay, basically 0% and 10% respectively. And they're also the most influential points in the data set in terms of the largest Cook's D. Okay, so this point and this point. Now, it depends really on what our intention is as experimenters here. We've looked at, if I page up to the plot of the data, okay, so we've got I8 values that go from 0 up to 10%. And so we're doing an experiment. Sorry, I'm pausing for a second because my cat is stepping over my laptop. I don't want him to press any keys. All right. So we did a range of experiments from 0 to 10%, and we want to understand the relationship with cloud point. Now, it's possible that we wanted this entire range from 0 to 10% for I8 values. It's also possible that we wanted to understand the relationship well enough because we typically will operate within the range of, say, 1 to 9% or something like that. So it really depends on the way we're going to use this information of what decisions we make next. Now, our most influential observations are this lowest point at 0% I8 and this highest point at 10% I8. So what do we do? So I'm going to page down, and I've got that discussion here. So first and last observations have the lowest values of I8, and they're the most influential points. So if we delete these cases and redo the analysis, we will find, in fact, that the cubic term is not significant anymore. And so it really depends on whether that's how we're going to use it. So in this case, we might restrict, let's assume that that's the case, and that we're in control of our experimentation and we're fitting this model to fit our needs, and that we'll restrict our range for percentages of I8 between 1 and 9. So here I'm just removing the points from the cloud point data set. I'm excluding the points of the minimum value of I8 and the maximum value of I8. Here's the OR pipe symbol. And then I'm refitting in cloud point 2, just the second data set, the same cubic model. And when we look at the summary here, we find, in fact, that the cubic term is not significant. Okay, so that cubic portion, so that lazy S, basically was determined only on those most extreme observations. All right, so that is the first example. By the way, 99% R squared for this model. So if you also look at the residuals for this model, which I did not include, they look great. So I recommend you looking at that. So the main point here is that how sensitive a polynomial model can be to one or two observations can drastically change the model fit. Okay, and which model is suggested. So that this starts curved down and then curves up at the end. That's basically the only information is from this one point and maybe the second point here. So if you include only starting from this point up to this point, that has a nice simple downward curvature to it, and a simple quadratic fits that just fine. All right, so I'll come back in the next video and we'll look at a more complicated model where we have both I guess in this case we've got actually two predictor continuous variables, and we're going to take squared terms for both x1 and x2.